Dear last speaker, mute your microphone. Okay. So, well, this is Sam Shan, and I'm introducing today's speaker. This is our, according to Jose, this is our first CSRC Zoom curriculum. So this is good. We since that everything the Zoom is working well, and today we have a speaker, Marty Morzfeld from SIO and the IGPP USSD. So Marty received probably that degree from Germany is equivalent to our bachelor degree in mechanical engineering, and then he did a PhD in Berkeley and also in mechanical engineering, and then did a postdoc in mathematics, and then become a math professor at University of Arizona, and then he moved here to SIO last year, and he's really interested in extremely participating in the joint PhD program between USSD, SIO, and SDSU in neuroscience. And of course, his expertise in computing will be really, really good for CSRC, and also, of course, for the math and stats department. And so today he will talk about Bayesian inference and how is that used in the earth science. Marty, it's yours.
Thank you. Thanks for meeting with me over Zoom and giving me the opportunity to talk here today. I must say that I have a 2-year-old daughter who might interrupt from time to time, but we're trying to keep that to a minimum. And also, if you look at this slide that is up right now, you see that it still says that I'm at the University of Arizona. So I updated many things about the slides, except the first slide. I was blind to it. So I moved here in early January from Arizona and switching from the math department to SIO. Okay, so I want to start by reviewing Bayesian inference as a way of merging models and observations by looking at a pretty simple cartoon. So I have here a mathematical model, which is a differential equation. So is dx dt is equal to f of x. F is some given function. And then I have an initial condition x0 is equal to x0. And if I'm given those ingredients, I can solve that equation, most likely numerically. And then I can plot the solution x, which I will often refer to as a state, as a function of time. And in the cartoon, that is the the brown line. And then if I take myself seriously and I realize that this is a model, then it should be a model for, say, Earth's atmosphere or another process or engineering type application. And then I would be able to also obtain some measurements or observations of the process that I'm modeling. And then I can represent these observations in the cartoon. And I use red dots to do that. And then these observations might have their own set of issues. So they could be, my sensors could be false from time to time. There could be some kind of noise on the observations. And in the cartoon, that is represented by these error bars that you see. And now if you look at the mathematical model represented by the brown line and the observations represented by the red dots, you see that there is some mismatch. So especially towards the right part of the plot, you can see that the prediction of the model is far from the observation, and far in this context means that it is far outside the expected error bars of these observations. And the idea of doing Bayesian inference is now to fiddle with the model. For example, you could try to find a slightly different initial condition so that the model trajectory is compatible with observations in the sense that it passes nearby the observations, maybe to within the expected error bars. And in the cartoon, that will be represented by the blue line. So that would be a good solution to the problem. Now you have a model that is actually compatible with the observations. An even better solution would be what is represented in the cartoon here by this yellow cloud, So you could think of, for example, computing a large number of possible initial conditions, all of which lead to state trajectories that are compatible with the data to within the assumed errors. So in the cartoon, that is this yellow cloud of trajectories, and it's in some sense a better solution to the problem because it doesn't just tell you where you think the model state should be at any particular time, but it also tells you something about how confident you can be in your predictions. And then with some luck, the actual physical state that you're modeling should be well within that yellow cloud that you have computed. So that is those are the basic ideas of Bayesian inference, represented by a cartoon. If you go a little bit more mathematical, you can describe most of it by a relatively simple equation. So I'm just going to write the observations generically by y. So that could be typically it's a large vector. And then my model, I can use a fancy m to represent. This is say the numerical solution of my ordinary differential equation or partial differential equation. And the theta, or the model parameters, are everything that I need to input into my model in order to obtain the solution. So that could be, for example, the initial conditions. And then I'm going to allow myself for some wiggle room. So there's another component, the eta, which is a model error. And often, I mean, that should be some stochastic object. It could be any random variable. A choice that is often made is that it's a Gaussian random variable with mean 0 and a given covariance matrix R. And then with these ingredients, you can now think of what is the likelihood. So it's the probability of observations given a set of model parameters. And you can write down what that is. And under my assumptions of a Gaussian eta, that likelihood is a Gaussian. You can write that down. Now, in addition to this equation, you may have some additional information. For example, if you're modeling subsurface flow, the model parameters could be a permeability field, and permeability should be positive. So you know that all of your parameters must be positive. That is some additional knowledge that you might have, and you would want to bring that into the solution of the problem as well. And that you can do by formulating a prior distribution. So if you have, for example, only knowledge that your parameters must be within some bounds or must be positive, then those prior distributions are often chosen to be uniform over these bounds or of the parameters that you have. And then you basically multiply the prior and the likelihood, and what you get is a posterior distribution. So that describes the probability of model parameters given the observation that you have collected. And that in some sense is the solution of this inference problem, because it describes the yellow cloud in this cartoon that I brought up earlier on. So this object of a posterior distribution is pretty interesting. And perhaps then not surprisingly, most of the numerical methods for solving inference problems are in one way or another connected to this posterior distribution. For example, there is a lot of work on optimization to solve inverse problems. And that you can often interpret in this Bayesian framework by finding parameters that maximize the posterior probability. And in that context, the prior takes on the role of what is often called regularization and optimization. And another way that you can solve these problems is by the Monte Carlo method, where you would represent this posterior distribution not by some function or one particular state, but you would represent it by a collection of samples or an ensemble. And in the hope then that if you take, for example, the ensemble average, that then this ensemble average would be an approximation of the posterior mean. And if you compute ensemble covariances or variances, those should be roughly equal to posterior variances or covariances. And I will focus on in terms of numerics, I will focus on the Monte Carlo method here. So to make this a little bit more precise, I'll give you a simple example, which I will talk more about later on. I will tell you where this equation arises and why it's interesting. But for now, it's just a version of the differential equation that I showed you before, except that this is a delay differential equation. So somehow I lost my cursor, so I can't really point at anything. But there is a delay. So this is a differential equation for the quantity h, and there are unknown parameters h0 tau. There's an alpha, and there is the delay capital T, and those are unknown. There's other quantity n. I assume that it's known. And one way to get at these parameters is to, given noisy measurements of A for some time period T, solve a Bayesian inference problem using perhaps priors that are based on parameter bounds, and then you can compute these a posterior distribution over these parameters. And then often the way that you can look at these posterior distributions is by a triangle plot. So on the lower right side, you see a triangle plot. It's just a collection of plots, and they are ordered in the form of a triangle. So on the diagonal, you see every one-dimensional marginal of this posterior distribution. So this distribution is over 4 parameters, h0, tau, alpha, and t. And on the diagonal, you see a histogram based on the Monte Carlo solution of this problem for the quantities h0, tau, t, and alpha. And then on the other plots are every possible 2-dimensional marginal of this posterior distribution. So this gives you an idea of how to look at a high-dimensional posterior distribution, and typically it's often it's in terms of these plots. And what you can see is that the posterior distribution is a well-defined bump in probability in parameter space. So these data or observations that were collected actually constrain the parameters pretty well. Okay, and now there is another flavor of all of this, which is called data assimilation, and that is mostly coming from numerical weather prediction. So you've actually you kind of interact with data assimilation on a daily basis, because the idea is to estimate the state of the global atmosphere. So that will be the model state, and you would do that sequentially, because if you're making a forecast for tomorrow, you probably want to take measurements of today's atmosphere into account. So I've prepared another cartoon here. So you make a forecast, and the cartoon is an ensemble forecast. So there are, I think, 5 different forecasts that you make. Now you collect a new observation. So you make observations of the atmosphere. You incorporate the expected errors. You perform an inference, and then you make the next forecast. And then this continues into the future. Now here the basic setup is the same. You're trying to compute parameters or model states given a set of observations, but now the prior is no longer a uniform distribution or some basic knowledge. It is basically based on the forecast from yesterday. So that makes it into a sequential problem, and it also makes many data assimilation problems different from other inverse or parameter estimation problems, because you have a pretty skillful prior already. So the prior here has a huge effect on the estimates that you get, because it is, I mean, a lot of work already went into today's forecast. So if you should make use of it, and that reflects in the prior, and then ultimately also in the posterior distribution. So these are some examples of Bayesian inference problems that I have some experience with. One is the global and operational numerical weather prediction. So there, an inference problem is solved every 6 hours, and the typical number of variables in a global atmospheric model is 650 million. And every 6 hours, you get between 2 to 10 million observations, depending on many things. That's why you have a large range there. So in any sense of the world, the dimension of this problem is very large. You have a huge number of observations. You have a very high dimensional model, and yet you can solve it if it has to be done every 6 hours. It means that you can solve that problem in much less than 6 hours. Other high dimensional examples that I've looked at is cloud index forecasting. That is important if you want to. It's important for utility companies, because they want to know where clouds are going to move on intra-hour timescales. Because when a cloud prevents sunlight from hitting a solar array, that can lead to very large ramps in the output of solar arrays. And then and so they want to know. So we looked at how can you make forecasts on intra-hour timescales for cloud index, which basically tells you how thick the cloud is in the sky. And that the dimension of that problem is much less than the global problem, but it's still about 10 to the 5. Also looking at geomagnetic forecasting on decadal timescale. So you want to, similar to how you predict the weather, you might want to predict the state of the magnetic field that surrounds us. And the dimension there is comparable to numerical weather prediction. I've also was involved in a DOE project that is about pulse-powered X-ray radiography, where the object of interest is a radiograph. So it's basically an image. It's a very high resolution image that has 4,000 by 4,000 pixels. So that's 16 million pixels, and each pixel is an unknown. So the dimension of this problem is 16 million. And there are many other high-dimensional problems that are being treated with Bayesian inference, but I can't list them all. So I just list some that I have some experience with. And then maybe luckily for us, there's also interesting low-dimensional problems. One is to connect phenomenological models for complex processes, and I will talk about that more in just a little bit. But there are, for example, if you know the Lorentz, the good old Lorentz model, the butterfly attractor, there are similar models that are representing reversals of the geomagnetic dipole field. And there are also predator-prey models for stratocumulus clouds. And I will talk about these two particular examples in just a little bit. Now, both problems are very interesting because they're both very difficult, but the difficulties are completely different. If you are working in very high dimensional problems, typically the most difficult part about the problem is the extreme dimension. If you are working in a low dimensional problem, a high dimension is not a problem because it's a low dimensional problem. But then you have issues if you, for example, want to connect a very simple model for clouds to observational data of clouds. It is not straightforward to do because the actual cloud processes are very complex. Your model is very simple, so there must be some kind of bridge that needs to be built between the two. And in general, the question is then how can you connect simple models with observations of complex processes? Okay, so now I want to give you a little bit more background on the numerical methods for solving Bayesian inference problems with two techniques called important sampling and Markov chain Monte Carlo. Many of you might know about this already, then it's a little bit boring. If you have not seen it before, it might be a little bit too fast. So the usefulness of this section is perhaps debatable. So I'll keep it short. And then afterwards, I'll show you two examples of this in action. And those are two low dimensional examples. One is connected to predicting dipole reversals, and one is connected to predator-prey models for clouds. And then I'll talk a little bit more about theory and the feasibility of sampling in high dimensions. And if somebody has a question, I don't know how you guys do this, but if you want to interrupt me, you can also unmute yourself and interrupt me if you want. Otherwise, I'll just proceed. Okay, so here's the very brief review of important sampling or Monte Carlo sampling. So now I take a step back and I'm just looking at a random variable x, which has a distribution p, and I want to calculate the expected value of x. Then that expected value is given by an integral. And the Monte Carlo approximation of that integral is pretty simple because it just says draw NE samples from the distribution p. If you want to compute the expected value, just sum them up and divide by the number of samples that you have drawn. Now I have again a cartoon for this. So the target distribution p is this orange bump in probability space. Now I draw samples from that distribution, and those are represented by these orange dots. And then if I want to calculate the expected value, which is the integral of x times p dx, I can just sum up my samples and divide by the number of samples that I have. This looks very simple, but it is maybe a little bit deceiving, because the step of actually drawing samples from a given distribution, even if you know everything about the distribution, is not possible. We know how to do that in a handful of cases. For example, you know how to draw a Gaussian samples from a Gaussian distribution. You know how to draw samples from a uniform distribution, log normal, and there's a handful of other distributions that have particular names. But if you go to a generally defined probability distribution P, it's not clear how to do that sampling. And in Bayesian inference, as I showed you before, the distribution of interest is the posterior distribution, which is defined implicitly by some complex numerical model and observations of, say, Earth's atmosphere. So it's definitely not one of the standard distributions that you know. And then this step of sampling is actually quite difficult. So what you can use is the good old trick of dividing and multiplying by the same quantity. So if I look at the expected value of x, I know is the integral of x times p of x dx. Now I can introduce a helper function, which I will call the proposal distribution q, and I multiply by it and I divide by it. So if I'm a little bit careful about not dividing by 0, this step won't change the integral. And now you can stare at it long enough and you can convince yourself that this is another Monte Carlo average, but of the function x times p over q, and average with respect to the proposal distribution q. So in short, what this does is it turns your usual Monte Carlo average into a weighted average, where the weights are the ratio of the target distribution and the proposal distribution, and the samples are drawn from the proposal distribution q. Now, since you have a lot of freedom on how to choose, you might be able to choose one that you know how to draw samples from, and then that sampling step is actually easy, and you pay for the fact that you sample q over p by introducing the weights w. You can also think of this in a cartoon. I have now here two distributions: the actual target distribution. This is the one that I'm interested in. I have that's in orange, and I have the proposal distribution q in purple. And I'm drawing samples from q, so I get the purple dots, and then I compute weights. So the weights are large when p over q is large. So that means that they are large in the region where there's a good overlap between p and q. And the samples that are in a region where p is small and q is large, they get a small weight. Okay, so that's one of the reasons why it's called important sampling, because not every sample is equally important, because they're drawn from the proposal distribution q and hence have an attached weight. You might wonder what happens if q is small and p is large, and that situation should be avoided. So a particular good approximation, a good proposal distribution is one that is a good approximation of the target distribution. I'll get back to that later on, of how to construct good proposal distributions. But there's a couple of pros and cons for this technique. One is that it's very easy to parallelize, because you can treat each sample separately. That means that you can use a different core for generating each sample if you want. And I've been involved in another DOE project in combustion chemistry, where they scaled up to hundreds of thousands of cores on one of the DOE supercomputers. So that's great, because it actually gives you a good idea of how to use these big machines. And I've also spent a lot of time on trying to find a good way to generically come up with good proposal distributions. And I've done that during my postdoc with Alexander Chorin in Berkeley. And the technique is called implicit sampling. And the basic idea is to draw samples by solving algebraic equations. Now, those are two good things, that there's a strategy for generating proposal distributions, and it's easy to parallelize. The problem is that there's a generic failure when you go to high dimensional problems. So I would not be able to recommend you to use an important sampling algorithm if your dimension is here I wrote 50, but I would actually be already skeptical if it's larger than 10. Okay, so now there's another technique for drawing samples from a given target distribution. It's called Markov chain Monte Carlo. It is similar to importance sampling in the sense that there's also a proposal distribution. But rather than drawing independent samples, you now have correlation between the samples. So in particular, you would start somewhere, and then you use your proposal distribution to propose a step to move around your parameter space. And then you introduce an accept-reject criterion so that you would accept or reject that step in a way that the Markov chain that you are generating with your procedure has a stationary distribution which is equal to the target distribution that you want. Now, that sounds a little bit complicated, but that's the main thing that is underpinning the MCMC. And it might also be easier to think about it in a cartoon. So here I have a probability distribution in the background. So where you see blue, that's very low probability. And then when it transitions to white, yellow and red, that's higher probability. And the dark red in the middle is the highest probability. So I've taken here 4 steps, and now I'm proposing a new step. And because this step is proposing to go to a higher probability, the accept reject criterion is likely to accept that step. So then I make that step, and then I proceed. And then if I keep going, I will first of all spend most of my time in the regions of high probability, so that if I calculate averages, I get a good approximation of the actual average with respect to the target distribution. And now you can look at the literature, and you will find many MCMC samplers, and they're all different because they're using different proposal distributions. You can also parallelize MCMC to some extent, but it's harder to do than importance sampling because you have this a feature of that you need to know where you currently are in order to propose the next step. So it's not as parallelizable as importance sampling. And it also has issues in high dimensions, which are perhaps less pronounced, but it's definitely difficult to solve a problem of dimension 100 or larger with a generic MCMC scheme. And I will talk about that more towards the end of the talk. Okay. Now I have Sam. How much time do I have? Do I talk until 3:50? Somebody listening?
Yeah, about 50 minutes, 45, 50 minutes. So about 3:50.
Okay.
Good, and then people can ask questions.
Okay, good. That's what I keep an eye on the time. Very good. So I'm going to use all of this now to try to predict and understand dipole reversal. So if you probably know that our Earth is surrounded by a magnetic field that is largely generated by the flow of liquid metals in Earth's liquid core. And then that field is a pretty complex object that varies over many spatial and temporal scales. But a very prominent feature of that field is that it has a strong dipole component, which is why you can use a compass that will point northwards. Now, if you had a time machine and you travel back about 800,000 years, and you look at your compass again, it would point in the opposite direction as it points today. And the reason is that the magnetic dipole field has undergone a reversal. So that if you look at the time series plot there in the upper right part of the presentation, you see paleomagnetic data, and on the right side at time 0, that's today, and the -2 is 2 million years ago. And then you see that what is plotted is the strength of the dipole field, and the sign encodes the polarity. So you can see that the intensity of the field fluctuates, and then about 780,000 years ago, there is a change in the sign. So the field undergoes a dipole reversal, it fluctuates, and there's another reversal, and so on. And the goal would be to understand better these dipole reversals and also possibly predict when the next dipole reversal happens. Because if you look at the, say, the last 10 million years, you get a reversal rate of maybe 4 per million years. And the last reversal happened 780,000 years ago. So you might be overdue for a reversal. And it might be interesting to understand what are the conditions under which you can actually make a prediction about the next dipole reversal. Can you understand dipole reversals well enough to be able to predict them? And this is where low-dimensional models can be useful, because if you wanted to write down you know, a model that can actually represent all the temporal and spatial scales of the magnetic field, you would be you'll be in trouble numerically and computationally, because those models are called magnetic hydrodynamics, MHD, and if you want to run a realistic MHD simulation, you might be able to do it, but you wouldn't be able to do that over, or you would have at least some difficulty to run it over millions of years, which is the relevant time interval that you need to be able to simulate if you want to study reversals, because they happen on million years timescales. So you can say, well, maybe I don't need to know all the temporal and spatial scales that are going on, and I want to just focus on the dipole. And then French physicist Christoph Giesinger wrote down a set of 3 equations that may or may not look familiar to you, but they are basically a minor variation of the classical Lorentz equations. So you have 3 terms here, Q, D, and V, and there's a linear part, and then there are quadratic interactions. And the variable D here represents the dipole field. Q is the quadrupole, which would be the next term in a spherical harmonics expansion, but you can also think about it as every component of the field that is not the dipole. And the dipole field and non-dipole field are coupled by a 3rd variable, which represents the flow structure at the core. So that's the V. And then you set it up correctly and you pick your parameters correctly, and it becomes a chaotic system with 2 fixed points. So you hover around one of the fixed points. That's hopefully what you see in the cartoon. It is actually not a cartoon, that's a simulation. And then seemingly at random, you switch over to oscillations around the other fixed point, and then you trace out a strange attractor here. So this could be a model for geomagnetic dipole reversals. And if you numerically solve these equations and you compare it to the paleomagnetic data, you will see some similarities. And then on the right plot here, I did some cherry picking and picked a part of I call that model the G12 model, because it's Christoph Giesinger in 2012. So the G12 model, I picked one of its reversals, and then I put it on top of the most recent reversal of Earth's magnetic field as represented in the paleomagnetic data, and you can see that this looks quite good. So you can then say, well, this is where the story typically ends. So you have a model and it looks like the data, but the question is, can you actually make this into a quantitative tool rather than just a cartoon or a qualitative tool? And what are ways to find out? So the way that we try to answer these questions is by using data assimilation and Bayesian inference. So we would calibrate the G12 model to the Earth record over the past 2 million years using 2 data sets, which are called PAD-M2M and SIM2000. And then we're using the calibrated model for predictions of dipole reversals, not unlike how the weather is predicted. And then we also define a set of tests to assess how good our model really is. I'm gonna close my door really quick. Thank you. And here is here's this technique in action. So you see a plot where we are zooming in again on the most recent reversal, and in blue you see the data. There's a light blue cloud that is based on errors that are expected in the data, and then you see a red line that is the result of our data assimilation, and then the red line ends, and we're going to do a forecast. But we stopped in the past. So it's not really a forecast. It's a prediction of the past. But that prediction does not know anything about what actually happened. So you can now make a forecast. The forecast is for the next 4,000 years. And we make an ensemble forecast. So you see some purple lines. And then that's our ensemble. And you see, if you look carefully, you see an orange line. That's the average of the ensemble. And then you can go through the entire data set, and you can keep doing this. And you can estimate the probability of a reversal within this 4 kilo-year time window simply by counting the number of reversals within the 4 kilo-years within your ensemble, and you divide by the ensemble size. And in that way, the result is a time series, which is the estimated probability of a reversal within the next 4 kilo-years. And in this plot, this is represented by the red line, and you can see that the estimated probability of an upcoming reversal peaks whenever a reversal actually happens. So it looks good, but again, we would like to be more precise and figure out how good this really is. So one thing that we did here is to find out if the model is useful is to compare it to predictions that are done without the model. And one way to do predictions without a model is to use an intensity threshold. So the strategy here would be to predict a reversal will happen with probability 1 if the dipole drops below a threshold. And then you have to be smart about how you define that and compute that threshold. And then we make our probability-based strategy compatible with this purely data-based strategy by also thresholding the probability. So we would compute the probability threshold, and if the probability exceeds this threshold, then we would predict that a reversal occurs with probability 1. And we compute the thresholds for both techniques using the same methods. And then we can do a comparison. And then we saw that the predictions that are based on the data assimilation and the model are slightly more accurate and more reliable than what you get if you do not use the model and simply do an intensity-based threshold. So that would indicate that the model improves predictions and might be a useful tool for predicting a time window during which a reversal is likely to occur. Now, this is a very shortened version of this story. But if you wanted to know the full story, we have a paper that by now is already old, but it's in PEPI, and it's a 2017 paper, which I'll be happy to provide for you if you want to read more. Now, the next example I want to show you is a similar flavor in that you are using a simple model to describe a complex process. So I'll show you here is a satellite image, and you see some white and you see some black there. Whatever is white is a cloud, and when you see black, that means there is no cloud, and you actually see down onto the ocean. And now within this relatively big snapshot of a satellite image, you can see that the cloud field has some interesting characteristics. For example, there are relatively large patches where you see a thick cloud, and then there are patches where you have only these filaments of cloud, and you can maybe, if you squint your eyes, you can see that they are sometimes forming almost a honeycomb-like structure. Now, one way to model this, to model clouds, is to do a cloud resolving atmospheric model or a large eddy simulation, LES. And I show you here, I show you one. I don't know how good my refresh rate is over Zoom, but you can see that the simulation kind of transitions from a thicker or denser cloud field to one that has also this honeycomb-like structure of cloud filaments. Now, a large eddy simulation is a pretty complex simulation, maybe comparable to a full MHD simulation in geomagnetic applications. And just like Christoph Giesinger wrote down a simple model for the Earth dipole, other scientists have written down a very simple model that is supposed to also model aspects of cloud dynamics. In particular, they have written down a predator-prey-like or predator-prey type model for the cloud depth age. That's the one that you saw on one of my early slides. And the idea for using a predator-prey model here is that the rain acts as a predator for the clouds. So the rain basically eats the clouds. And the model that was proposed here is a scalar delay differential equation. So there's absolutely no spatial scale. And maybe you can find other models for cloud systems and build a whole hierarchy of models that range from a fully cloud resolving atmospheric model, or the LES, down to the predator-prey model, which is just one equation. And the question we wanted to ask is, how can we connect models of completely different type? So how do we connect, for example, a large eddy simulation to a predator-prey model for clouds? And again, we try to do this by using ideas of Bayesian inference. In particular, it would be good if we find a way to be able to calibrate the predator-prey model to a particular LES. And that would mean that we estimate the parameters of the predator-prey model based on an LES. So we want to take a large eddy simulation, which is gigabytes of numbers, and want to compress it in a way that it is useful to inform the 4 model parameters of the predator-prey model. And then if you remember that there's no spatial scale, for example, in the predator-prey model, one thing you could you need to be aware of is what is your predator-prey model actually modeling. And it basically is set up to produce limit cycles. So it can produce a cycle that it shows you how a cloud is growing and then how it is eaten up by the rain, so it disappears slowly. So the way to connect to an LES is to search through the LES and find cycles of cloud growth and decay in the LES. And there's 2 illustrated here on the snapshots of the LES cloud depth field. On the right, you see red squares where you see that a cloud builds up and then decays. Or cloud depth builds up within that red square and then it decays. And the same happens later on in the simulation at a different location in within the blue square. Now we extracted those cycles from the LES by doing a combination of spatial and temporal smoothing and basically cutting out these cycles. Let me just cut it short and tell you that we have a procedure which results in 463 cycles that we extracted from the LES. And they are shown in the plot here on the lower left. And you can see that there's some variation in the cloud depth cycles, both in their length and in their amplitude and in their overall structure. And now we have another procedure that gives you that basically generates a limit cycle or takes off a limit cycle from the predator-prey model. So given a set of the 4 parameters, we solve the delay differential equation for a given time, and we check whether or not we are on the limit cycle. And if we are, we stop and we find 2 local minima, and everything that is in between those 2 local minima is called a limit cycle, and that's what we extract. So now we can build a posterior distribution that connects the posterior distribution now connects the cycle that were extracted from the LES to the cycles that we observe in the predator-prey model. And then you can, I think I've shown you this before, but now you know what it is. So I show you here the triangle plot of that posterior distribution. So the large eddy simulation actually constrains the parameters of that predator-prey model. And the cycles that you get from the calibrated predator-prey model are compatible with or are within the variation of that you see in the cycle that I extracted from the LES. We've done a lot of robustness studies of our approach, so it seems to be robust to some of the numerical details and some of the assumptions that we are making. And in what it tells you is that this predator-prey model can actually be viewed as a simplified representation of some or more or less one aspect of the large eddy simulation, namely on how, on average, cloud patches grow and decay and that's the that's the extent to which that model can be useful. That could possibly be you can, now that you have a numerical and mathematical framework for connecting the two, you can ask more interesting questions, such as, when I vary the meteorological conditions in my LES, what does that do to the parameter estimates, and how do the parameters of the predator-prey model react to different meteorological conditions? And since these parameters actually have physical meaning, that might actually, in the end, tell you something about the cloud microphysics, and that's something we want to do. We want to do in the future, but haven't done yet. And now I want to just very briefly. So I have a few more minutes, right? I just tell you very briefly that it's hopeless to do important sampling, and you can see that from very simple examples. There's basically an exponential dependence of the required number of samples with the dimension of your problem. So it's hopeless, that important sampling technique that I showed you before. MCMC is a little bit better. If you apply it to a very simple problem of a Gaussian, for example, you can also figure out what a required ensemble size or chain length is, and that also increases with a dimension of your problem. It doesn't necessarily increase exponentially, but it can be linearly or even sublinearly. But still, if you look at dimensions of hundreds of millions, maybe such a scaling should be avoided. So you can ask yourself all kinds of questions of when you can sample in high dimensions. So let me just get to the main graph, just to give you an idea. So if you have a large array of problems that stretch very low dimensions to very high dimensions, so you have 10 to 10 to the 8. 10 is maybe your phenomenological models, the ones that I spend most of my time on today, and then 10 to the 8 is numerical weather prediction. Then you can definitely solve these 10-dimensional problems using MCMC or maybe even important sampling. The other problems you should avoid any sampling technique, because it's not going to work, because it has this dependence on the dimension. That is, if you don't assume that you know anything about the problem structure. For example, if I know that statistical interactions are local and I can make that part of my sampler, then I can get to much higher dimension. Also, if I know that my problem is Gaussian or maybe nearly Gaussian, I can get to even higher dimensions. And if you want to go to numerical weather prediction type dimensions, then you have to basically exploit during sampling every problem structure you can think of. So in that case, it's a nearly Gaussian problem structure and sparse statistical interactions. And the other option, when you can actually sample in high dimension, is if there is secretly a small dimension. So it's possible that you have a seemingly high dimensional problem, but everything happens on a dynamic manifold that has a low dimension. Then that sampling is also not a problem if you can find that a manifold. There's an analogy to linear algebra. If you think of just solving AX equal B, then you can do that with a direct solver. If you go to high dimensions, you can do that if the matrix is low rank. So that's what I mean by a secretly low dimension. That would be the equivalent in the sampling problem. Or if you have a high rank matrix, then that matrix hopefully is sparse. Then you can also go to extremely high dimensions, and that's a sparse statistical structure that we're discovering now. What is going to happen is that interesting problems are all in the middle, and then we really don't know what to do. So with that, maybe I skip my summary and just thank you for seeing me on Friday afternoon on Zoom. And I have a lot of references. So if you want to read about this, I can send you lots of papers. So that's maybe with that, I just stop talking and let you guys ask some questions.
Great, thank you, Marty. That was great. Thank you. So questions, audience, please. Well, Parisa, could people raise their hand? There is a function called raise hand. So Marty, your computing for these two examples, could you just, if students want to learn how your technique, what kind of kind of infrastructure do they need? Can they do this all need to be done on supercomputer, or they actually can be done on the PCs?
No, so in part, I think that the simplified models are very useful exactly also for that purpose, because I can, for example, if I have a Lorenz 63-like model, I can learn about all kinds of data assimilation problems on my iPad if I wanted to. Right? If my iPad would allow me to code, but definitely on a computer. For example, I have a MacBook Air that is not powerful enough to do a virtual background in Zoom, but I can definitely solve a Bayesian inference problem on it if I don't go to an extremely high-dimensional problem. So there is no infrastructure needed. I think it's always a good idea if you learn how to use a big computer early on. So I would definitely, even if the problem maybe doesn't ask for it, I would still suggest to you to run your code on a bigger machine or on a cluster, just so you learn how to do that.
Okay.
But there's, if there is a range of different complexity in the models, there's a range of computer architecture that you need to solve those problems.
Now, did you write your code in what language did you write your code in?
So this code for the large eddy simulation.
Yeah.
The large eddy simulation, I have not done that large eddy simulation. That was done by people at NOAA, and they gave us the result of that. And I don't know what language they're coding in, but that's a big simulation that runs on many cores, and it's its own artistry. But the MCMC and all the plots that you see here, and the solution of the delay differential equation and all that was just Python. Okay. So that you can do it in Python. And I write a lot of code for example, everything connected to the dipole modeling was all written in MATLAB.
Okay.
But for example, the combustion chemistry problem that I mentioned earlier on, that was a combination of Python and C++, which everybody who was involved in that problem said that was not a good idea. And mixing the two was maybe not the smartest thing to do. But I hear that is often, more and more often done. So again, there's a range. And it usually depends on the problem, right? In the combustion chemistry, there was no choice for me, because we used a lot of legacy codes. Yeah. Some of the MCMC was already typed up in Python, and then all the combustion chemistry was done in C++. So there was some kind of mix.
Okay.
Yeah. I have a question.
Go ahead.
Can you hear me?
Yes.
Yes.
Oh, okay. Hi. Thanks for your talk. I do work in a area where, so all of these things that you're talking about have very strong time correlations, right? Like one point is related to the next, is heavily correlated to the next point, right? Because there's the because these are like dynamical systems, right?
Yes.
So in my case, we don't necessarily have that. It might be completely different. I'm wondering if well, at least, I mean, there are correlations, but they're complicated, and I'm curious if these methods rely on those correlations in some way, or how does that determine, like, if you were given a problem that didn't have that, you couldn't necessarily assume there were strong time correlations or something like that, does that affect the method?
No. So let me go through my slides. So there's two flavors of this problem. If you're working with a dynamical system and your observations are coming in sequentially, then there is time ordering galore, right? Your model has a natural way of stepping through time, and your observations are coming in a time ordered way too. In that case, it would not make sense to not make use of that time ordering. So there's a lot of effort that are going into reusing what you just learned, and not, you wouldn't want to, in such a problem, you wouldn't want to start always from a very broad and uniform prior, because you already know something about the parameters, because You've just modeled them very carefully and as carefully as you can to be able to come up with a forecast. If you go to a more generic Bayesian inference or inverse problem, there does not need to be any ODE involved. In fact, I can show you many examples where there's not even an ODE involved. For example, you can do spatial statistics, right? And then you can use those techniques to just estimate spatial fields. And I can send you one of my papers if you want that has an example of this type in there, and you can see if you find it interesting or not. Now, many of the geophysical questions that I'm interested in, they do have some kind of sense of time in there. So for me, it's difficult to just come up with a good example that doesn't have time in it, other than this one particular spatial statistics thing that I looked at. But there's definitely a lot of work going on problems where you don't have, maybe time doesn't play any role, and you could use, in principle, the same techniques. It would affect how you choose your prior, though.
Sure. Yeah, that makes sense.
Reuse old information.
Thank you.
Yeah, no problem. Thanks for the question.
Thank you.
I have a question.
Mm-hmm.
So when you talk about the dimensions in the inference, I mean, do you mean the variables, the number of the variables?
That's a very good question, and it's not easy to answer. So I was hoping that nobody would notice that. So no, of course I would hope that people notice it like you. So look, the thing is that because you have several ingredients here in your problem, you have the dimension of your parameters, right? So that could be large. For example, if your parameters are the initial condition for the global atmospheric state, that's 650 million variables that you're estimating. That's huge. Now, another dimension that is important is the number of observations that you have. So the problems get harder if the number of observations is large, because if you look at this equation here, can you still see my screen? Yeah.
Yes.
Yeah, sure. Okay.
Can you see my cursor now, my mouse? Okay. So you see here the posterior distribution, here's a prior, and here's the likelihood. So you can think of it as the prior being transformed by the likelihood to the posterior distribution. If I have some prior, and then I just have one observation, for example, one temperature measurement in San Diego, that is not going to deform this prior very much, right? So then the problem of solving this, or of drawing samples from this posterior distribution, not as difficult, because the posterior distribution is basically your prior distribution. So it's a collection of things that actually go into the relevant dimension for this, to kind of an effective dimension that is relevant for describing the complexity of these sampling problems. Another thing that is important is this error covariance R. If that is very large, then the likelihood again does not have a huge effect, and the posterior might look very much like a prior distribution. In which case, you also don't learn anything about your parameters. So you might not want to solve that problem, but that would be an easier problem. So just to summarize, yes, the dimension question is important, but there are problems where that question is also if you look at the numerical weather prediction problem, every dimension you can think of is large. So very likely an effective dimension is also very large. So and then there's other problems where that might not be true, but it's a delicate question. It's a very good question. But generally, when you hear people talking about a high dimension, they typically talk about a mix of number of observations is large, and the number of state variables or parameters that you're trying to estimate is also large.
Okay, thank you. I have another short question.
Sure.
So you have the hot spots for each parameter. So when you decided which parameter is the optimal, do you estimate the hotspots for each parameter separately or considering the model as a whole?
I always think
Yeah.
that I was successful with solving the problem if I have enough samples that I think that they can be used to compute properties of the posterior distribution. So now if you ask me what parameter should I use, that depends on what the shape of that distribution is, right? If it's, for example, a bimodal distribution that has two well-separated modes, and then I would suggest to you to use the mean, then you should never talk to me again, because that would be a very bad advice, right? Because the mean would be in between the two modes and it would be a very useless estimate. So you should pick one of the modes, for example, in that situation. If you are looking at something like this on my screen here, maybe you should again use the mode as your parameter estimate. And if there's more than one mode, maybe you should ask for more data so that one of them disappears, or you should ideally report the location of the modes and also some estimate of their width in terms of a variance or covariance that goes with those modes.
Okay, thank you.
No problem. Was that an answer to you? Maybe I misunderstood your question.
Yeah.
Okay.
I think you answered my questions.
Okay,
Thanks.
good.
Okay, good. Any other questions?
So actually, I have a quick question.
Sure.
The question is about when you do the dipole reversal problem simulation, do you need to consider the Coriolis effect caused by the sun?
So this model that we consider definitely does not have that in there. And I think that the typical MHD, so the typical MHD would just do the field that is generated by the flow at the core. And it would not necessarily also consider interactions with other fields or, solar winds and all that stuff. There's also a field that is maintained just by the magnetization of the crust of the planet. Okay. And that I think is also, you have to take into account separately. So if you look at, here, this is some kind of artist illustration of the field, and you can see that it's bent and these field lines are, that doesn't really necessarily look like a dipole field. But if you are going for an MHD or one of these simulations, I think you focus on the field that is just generated by the flow of liquid metal.
Okay, so you don't actually consider the rotation of the Earth itself and also the rotation of the Earth with respect to the sun. No.
No.
Okay, I see. Okay, thank you very much.
Good. Well, many good questions. So, well, Marty, so in the future, we'll get you to come to SDSU more often.
Yes, you were promising me a happy hour after that, I think.
Yeah, sure, yes.
We'll have to do separately now. Yeah, I was looking forward to coming. I'm glad that I could do the Zoom, to at least people have seen my face in my bedroom. But I'll be very happy to come over, and I like to stay connected to math departments. I like mathematics, and I want to keep in touch, and we can talk about students and all that. Great. I look forward to that.
Thank you very much. Jose, do you have anything?
Yes, I just want to thank you, everybody, and Matt for his great talk. That now we know that where we're getting when you come to campus next time. So
yes,
definitely the happy hour is still on.
Okay, good. Yeah, I look forward to it. I'll definitely come back. It's near, and I'll be happy to come out and you guys. And then yeah, well, what I want to say is, I'm sorry, I wanted to really talk more about the high dimensional stuff. So that could be a good excuse for me to come back, right? Because
exactly.
Now I messed up. I only talked about the simple models. I want to talk about the high dimensional stuff maybe next year or something. whenever it
Okay.
makes sense. Okay, I
Sounds
would be
good.
very happy to get. I would also really like to get to know you guys better. So it would be nice to spend the whole day and maybe talk to you and see what you're up to. Okay? It would
Absolutely.
be great.
But take care.
Very good. Good.
Bye.
I'll take care.
Thanks a lot.
Peace.
Okay.
Yeah. Okay, bye-bye. Have a good weekend.
Bye.
Bye.
Yeah, you too. Bye bye.